Hello smart apes. You've probably heard that the four forces in the universe are gravity, electromagnetic force, strong and weak nuclear forces, right? Not quite. I'm sorry to break it to you, but gravity is not a force. Let's start the video with an analogy. You are falling. What are you going to feel? Nothing. No gravity. And if you are at the middle of space? Exactly the same. In both situations, you are not experiencing gravity, and if you push an object, they will move away in a constant velocity. You are an inertial observer. In your point of view, no forces are being applied on you, and there is no way to distinguish in what situation you are. Einstein said that these situations aren't similar, they're the same. Want a way to see it? Buy glasses. Just kidding. Imagine that you are in space and start falling into a planet. When would you start feeling the gravitational pull? When you hit the ground. Until then, you won't feel anything and will remain an inertial observer. But if gravity is not a force, then what is pulling you to the planet? An illusion. You are moving in a straight line, but not in a straight space-time, because matter curves space-time, and the planet that is attracting you is just curving the straight lines in which you're moving into. John Wheeler once said, matter tells space-time how to curve, and curved space-time tells matter how to move. Imagine that you and other person are always moving in one direction in a sphere. At some time you will touch, your paths will cross each other. Just like some force was attracting you too, because even thought you were moving in a straight line, you were moving in something curved. Another good way to see this is mapping a straight line in a map. What you will see is that the straight line is curved. Those lines are called geodesics. Interestingly, that's also what you call the paths taken by inertial observers in curved space-time. Now imagine that you are on a spaceship and it starts going faster. For somebody outside the spaceship, you will look stationary, while it accelerates into you. To you, you will feel like you are falling to the ground of the spaceship, like you are feeling right now, if you are not in space. Like the force of gravity is applying to you, but again, gravity is a fraud. Back to the spaceship accelerating. To you, you're stationary, but you're feeling gravity, and so you aren't an inertial observer. To say at what speed you're moving, you need an inertial observer. In Earth, to an inertial observer, everyone is moving at 9.807 meters per second up. I hope you're starting to connect the dots. If not, here's the explanation. You can't go on your straight line because the floor is stopping you to do so, and that pushes up on you, making you feel like you're being pulled down, like in the spaceship. But if all points on Earth are being pulled away, why isn't Earth exploding? In general theory of relativity, you can be accelerating and don't move at the same time. Imagine that you are at your spaceship, and you turn a flashlight on. Light will move in a straight line, but if the spaceship is moving, then in the time that takes light to reach the other side of the spaceship, it would have already moved, making light seem curved. If the spaceship is 10 meters long and I'm moving at 100 meters per second, by the way, a lot, light would move a total of 0.00033333564 meters, or about 3 eukaryotic cells long. In Newtonian physics, you aren't accelerating, but a falling piano is. In special theory of relativity, the piano is just moving in a straight path, while you are accelerating and standing still. Goodbye smart apes.